Hello and welcome to Dr. T Math. In this video I am going to show the factor remainder theorem and the rational roots theorem, and then look at some graphs of polynomials to kind of get a better eyeball view of what's going on here with roots and extrema and how that relates to derivatives and their slopes. So we've got a big long polynomial here and it's kind of messy and maybe we want to factor it. And then the first thing we're going to have to look at in trying to develop a strategy for factoring out this giant thing here is looking at the factors of the first leading coefficient and also the constant at the end. And so since the leading coefficient is 1, what we're left with is the integer root theorem. If this constant at the beginning, if the coefficient at the beginning wasn't 1, then we'd have some fractions as possible factors, but let's look at 192, do some prime factorization like we did in the previous video. 192 divided by 2 is what? 90 and 6. 96 and 2 divided by 2 again. We're going to get 2, and 96 divided by 2 is 48. Divided by 2 again. We're going to get 24. Divided by 2 again. We're going to get 12. Come back up here, 12. Divided by 2 again, we get 6. Divided by 2 again, we get 3. So we've got, let's count our 2's. 1, 2, 3, 4, 5, 6. We get 2 to the 6 times 3. It's prime factorization. Let's just double check that. Looking on a calculator here. 2 to the 6th. 2 to the 6th times 3 is in fact 192. So that's good. Now let's go ahead and list out all of our possible factors. And so then we're going to get something like all of these powers of 2, it's going to be a whole lot of different numbers, but plus minus 3, plus minus 1, plus minus 2 there, and then we're going to have to go through all of the powers of 2 up to, and all the powers of 2 times 3 up to 192, and it's going to be a little bit exhaustive, so we're going to skip through some of this. We're going to be 4 plus minus 8 plus minus 16 plus minus 32 plus minus 64, and then all of those times 3, which is going to be plus minus 6 plus minus 12 plus minus 24 plus minus 48, and then that's going to be all of it. But of course, we know already that some of these are not going to be roots because that would just be too many roots for a polynomial order 5. And so the main idea here is sometimes it gets a little bit less convenient to factor some of these things out. But let's just say there is a graphing calculator. that's always possible. And so we go ahead and graph that, and the graphing calculator can also factorize for us. So what we're left with is x minus 3, x plus 4 squared, x squared minus 4. And then, so x minus 3, x plus 4 twice, and then x squared minus 4 is going to be x plus 2 and x minus 2 back here. And we can see that's basically what's going on here. So graphing calculator certainly made life a whole lot easier, although, as I said in a previous video, those A-level British math folks sure don't like the idea of there being a graphing calculator in this world. So we've got a double root here at -4, and that corresponds to that one right there. That's what our squared means. We got x plus 4 equals 0 twice. That means x is equal to -4. Here we got x plus 3 is equal to 0, so x equals -3. I'll go back here, that's -3. Notice there's nothing in there, though. Notice there's nothing in there. And we could get into the reasons, why that is. The reason why that is in this case is because I exchanged the plus and the minus. That's why that is. So we got x is equal to positive 3. There we are. That's better. And so next up we got x is equal to plus and minus 2 for, get rid of that one, x is equal to plus and minus 2 for here and here. Okay, so now we found the roots, and we could have done that a couple of different ways. You know, back in the old days we would have had to try to factor this thing by hand, and that would have been a real pain. But let's go through the motions and see if we can come up with some sort of indication that we're on the right track. So we would have had to try plus and minus 3, but let's just for simplicity and expediency's sake say that we tried plus 3 and it didn't work. And so we're going to be looking at x to the 5th, what is it, plus 5x to the 4th, 5x to the 4th, minus 12x cubed, minus 64x squared, 68x squared plus 32, 32x plus 192. And that's a whole lot of numbers to do long division, but what we're interested in with long division is this thing right there and that thing right there. We could do synthetic division, but I'll leave that for another day. Okay, so how many times does x go into x to the 5th? We're going to be left with x to the 4th. Now we're going to multiply x to the 4th times both of those things, just like long division. We're going to get x to the 5th minus 3x to the 4th. And we're going to subtract these just like we would regular old long division. That one's gone. And we get minus a minus is a plus, so 8x to the 4th. Drop down the next thing, just like regular long division. How many times does x go into 8x to the 4th? Well, it goes in plus 8x cubed times. Multiply that over here, we get 8x to the 4th. 8x cubed times negative 3 is negative 24x cubed. Subtract that. Get rid of that first thing there. And minus a minus is a plus, so we got plus 12x cubed. Plus 12x cubed. Drop down the next thing, minus 68x squared. How many times does x go into 12x cubed? It goes into 12x cubed plus 12x squared times. And we're going to multiply back here. 12x squared times x is 12x cubed. 12x squared times negative 3 is negative 36x squared. Subtract that. Get rid of these, since a minus and a plus cancel each other out. Minus a minus, we got negative 68 plus 36. The difference between 68 and 36 is 32, and so we're going to be left with negative 32x squared. It's getting convenient now because we're dropping down a plus 32x, plus 32x. And how many times does x go into negative 32x squared? Well, it goes in minus 32x times. Minus 32x times negative times x is 32x squared. And then we're going to take and say minus 32 times negative 3 is going to give us positive plus how many? 96 plus 96x. Subtract that, just like regular old long division. Minus in, oops, sorry, we got minus in here. Minus a minus is a plus, so these two cancel out. And we've got 32 minus 96. The difference between 32 and 96 is 64. And we already did 64. We found 64 times 3 is equal to 192, so it looks like it works out. So 60 minus 64x. How many times does x go into minus 64x? Well, it goes in negative 64 times. And then we're going to add to that 192. Oh, forgot to drop down. Plus 192. Got that drop down. Then we're going to multiply out here, x, and we're going to add 192, subtract that parentheses, and we get a remainder of 0. Well, that was a long and drawn-out way to do what the calculator does in just a moment, which is why those British A-levels maths people are living in a time that does not exist, if you ask this guy. At very least, we should get a graphing calculator, because then we can go on to bigger and better things rather than spending all our time doing stuff that has been done a billion times before. And so we would then take that, if we were doing it the old-fashioned way, which we aren't, we would then take that and go through all those motions again using all of these potential integer roots, and it would take just about forever. But in fact, we've got graphing calculators which are here to help us. So we can see very well that the roots are right there, and the graphing calculator will identify those roots too if we ask it using this root function here, that root command there. But what does it mean? Well, what that means is that at this part of the graph, y is equal to 0. So the dependent variable is 0, right? So it depends on what the actual situation is, what that means as far as words go. But in mathematical terms, the dependent variable is 0. And this could be, again, this is a little bit abstract, but it could apply to many thousands and millions of situations, just depending on what we're talking about. Polynomials do exist in the real world. You can do a Google search on that one if you want. In this slide, we're looking at the derivative of that function laid over that function, and we can see that in this case, this is a special root. This is a special root, and you can see that this is the only root which has the derivative of the function going directly through it. And that is because the slope of the original solid line function at that point, -4, is 0. And it is 0 because we are at a relative maxima. We're at a local maxima there. We're at one of those extrema. And that's when, luckily this polynomial illustrates this point perfectly, that's when the first derivative is going to be equal to 0, when the slope of the function is 0, because the first derivative is the slope. That's all it really is, the rate of change. And then we can see that the function is 0 again here, which does not correspond to the first derivative being 0, right? So when the function is 0, the first derivative can be 0, so sometimes, but it is definitely not always 0. When is the first derivative 0? The first derivative is always 0 when the slope of the function is 0. And so that's how we find the maxima and minima. Right here, up top, right there, right here, and coincidentally in that case, right there. And so this might be a question about maximization or optimization, right, or minimization, if you're looking at the troughs. So the first derivative, that's the slope of the function, it is 0. It crosses the x-axis when the function itself has a slope of 0. And for polynomials, there are many places. There might be many places where the slope is 0. Those are those peaks and troughs. And then there are more important parts too. If we wanted to sketch in second derivative, we would see that when the second derivative is 0, that's when the slope of the first derivative is 0. And then you can see right there, when the slope of the first derivative is 0 at those peaks and troughs, then that's what they call inflection points. Those are inflection points. And for whatever reason, the graphing calculator that I'm using here, the TI-84 emulator, only showed those two. And then if I move the graph a little bit, it would show this weird sort of line between those two there. But when and we could carry on that pattern over and over and over. When the slope of a function is 0, then its derivative crosses the x-axis. So for the original function, the slope is 0 there, the first derivative crosses the x-axis. For the original function, same thing. Same thing here, there, same thing here, is right there. Now, if we look at that first derivative and we'd plotted a second derivative on there, that means that when the slope of that first derivative is 0, the second derivative would be crossing the x-axis, would be right there. When the slope of the first derivative is 0 at those peaks and troughs, the second derivative would be crossing the x-axis right there. And you can see there's one fewer root for each derivative, because as we take derivatives, if we had an x to the fifth function to start, then its derivative is going to be one less. We're going to reduce the power of the leading term each time as you take derivatives. And so there will be one less root. And so there's also a connection between the peaks and troughs of the first derivative and the inflection points of that original function, where the inflection point is the point at which the slope turns from increasing to decreasing. Now the slope is still positive around negative 1.18. The slope is still positive, meaning that the function is still increasing, but its rate of change, the rate at which it is increasing, turns from positive, so it's getting more and more positive up until that point, and now it's turning more and more negative, or it's turning more and more towards 0, and then it will go to negative until this point here, right about there, when it's increasingly negative, increasingly negative, increasingly negative, and at that inflection point it flips to decreasingly negative. So it's turning more toward the positive until it hits 0 again here, and then it would be increasing. After this point, you can see no more peaks and troughs on the first dotted line derivative there. And so after this point, that original function is only increasing. The slope gets steeper and steeper and steeper. And so there's a lot we can do with these graphing functions, the graphing calculators. You can imagine that if we were caught up doing the tedious work of Bicon era, like the British A-level maths people would have us doing, then we wouldn't really have time to do all this great intuitive and sort of conceptual exploration of these different graphs. Okay, so polynomials can be broken down into parts. That's a main theme here on Dr. T Math. The big stuff is made of small stuff, and that small stuff makes up the big stuff. And then once we find those parts, we can see that those relate to significant features of the graph. And the same goes for after we find derivative. Even if we don't know exactly what a derivative is, we can still interpret it as a polynomial function. And then these polynomial functions match up. The significant parts of these graphs match up to significant parts of the graphs of their derivatives. Okay? And in this case, those inflection points and those roots and those peaks and troughs are all related because the slopes are all related. Right? The rate of change is always related. And so whether we're talking about the rate of change or the rate of change, these things are still rates of change. Okay? This has been Dr. T Math. Thanks for watching.